Okay, so a covering space is called the universal cover if X tilde is a simply connected space. An example is this one, covering space of R, sorry, S1, which is R. R is, of course, simply connected, right? Pi1 of R is just trivial group. Therefore, it's a universal cover. Another example is the universal cover of S1 wedge S1. We know that pi1 is just the free group on two generators, let's say F2, actually generated by two elements, A and B. And the way we construct the covering space, universal cover, is the following. First, consider, one of the circles and open this to a real line. And then this circle, you may consider it like this. At each integer, you have a circle. And then you open up these circles and so on. In general, the way we construct covering space will be via the paths or homotopy class of paths. For example, consider this word in the fundamental group, A, B, A squared, B. That will correspond to the following path in the covering space. I go 1 unit in A direction, and then 1 unit in the B direction. But if this letter has, if this letter corresponds to a side of length 1, the next one will correspond to a side with length 1/2, and so on. So I go 1 unit like this, half unit like this, and then quarter unit, and then 1/8 unit, and so on. So this way, I will obtain a path, and that path will correspond to this word. And this thing will be a tree. And we know that trees are actually simply connected objects because they have no loops in them. And we have a map from this tree to S1 wedge S1. How it is defined? Well, every point here actually, is on these paths, and this gives me how the map is defined. This will just this corresponds to the circle A. So from this point to this point, I'll just go over A, and then B, A, B, and so on. Okay, so these letters tell you how the map is defined. So this is the universal cover for the S1 wedge S1. And our aim is to construct the universal cover covering of any given space. And video biraz garip çalışıyor ama. Okay. Theorem is this. Let X be a path connected locally path connected and semi-locally simply connected space. Pardon, path connected. So it will be path connected, locally path connected, and semi-locally simply connected. Then X has a universal covering space. We have seen path connected and locally path connected before. What is this semi-locally simply connected space? Locally simply connected is like locally path connected. So every point, given a neighborhood of any point, there is another neighborhood of that point which is simply connected. That is locally simply connected. So locally simply connected means the following: given any point and a neighborhood, open subset, there is another open subset, so that X is in V, V is contained in this U, and V is simply connected. Okay, V is simply connected. Yes. That is locally simply connected. Semi-locally simply connected means the following: instead of assuming that X is simply connected, we assume the following. So semi-locally simply connected space is the following. Whenever a point is given and a neighborhood is given, there exists another open neighborhood, so that X is in V, V is in U, and you don't assume that V is simply connected, but you assume the following: the map from pi1 of V into pi1 of X is trivial. So this is the map induced by, let's say, I star is trivial. This homomorphism is trivial, where I is the inclusion map. Of course, if V is simply connected, then this fundamental group is trivial. Therefore, the homomorphism will be trivial. So this is something simpler than being locally simply connected. It's you just require that this homomorphism is trivial. Okay. Let me just tell you how this is proved. Kameraya bir şeyler olmuş ama. No, you don't know. You know, this is simply connected. Then you know, this map will not be trivial, right? Idea of the proof. or sketch of proof diyeyim. I will not, do every detail. It's quite long. The idea is the following. Recall that a space Y is simply connected if and only if and only if for any 2 points x, y in y there is a unique homotopy class of paths joining x to y. And here homotopy is required to fix the endpoint. So simply connected space is something like this. Suppose I fix one of the points of y, then for any other point y, let's say, there is a unique homotopy class of paths. Okay, therefore I can parameterize actually the points of this simply connected space with the set of all homotopy classes of paths in this space, where homotopies fix the endpoints of the paths. Tamam mı? Yani burada şimdi uzayın ne olduğunu bilmeden so we are trying to build the covering space without knowing, how this space look like. If it is circle or just wedge of 2 circles, then I can, draw a picture of the covering space and try to describe it. But if I am given an abstract space, what is the simply connected covering space of this gadget? So you have to build the space so that it should work for any given space. And the idea is, if you have a simply connected space, then you can just parameterize the points of that space with the set of all homotopy classes. There's a one-to-one correspondence between the homotopy class of paths joining those points to y0 and the points y. Okay, and then we do the following. If this is the universal cover, let's say this is the universal cover. Then we know the following. So points of this space corresponds to homotopy classes of paths. Let me choose a base point here and a base point here. Okay. Every point of x tilde corresponds to homotopy class of a path. Okay. And every path, of course, has an image down here obtained by projecting it via P. And what we know is the following. Every such path actually is the unique lift of this path starting at this point. Therefore, the homotopy class of And also, if I have a homotopy of this path, let's say this path is homotopic to this path, then since there is already a lift of one end of the homotopy, this homotopy has a unique lift. Therefore, you have a homotopy here. And since these two are homotopic, why the ends are, no, this endpoint doesn't have to be the same. So it might be something like this. No, but if these are homotopic, then the endpoints should be the same, right? Yeah. Yes. The endpoints should be the same. Nasıl? Tabii. Şöyle, let's call this gamma 1, gamma 2. This is gamma 1 tilde, gamma 2 tilde. These are homotopic means I cannot say that they represent the same thing in the fundamental group because these are not loops. They are just paths. So these are homotopic in the class of all paths joining this point to this point via homotopies, keeping the endpoints fixed. And these two are homotopic and these two are homotopic. But the thing is that the homotopy classes of paths joining x0 tilde to any other point in x tilde is the same as homotopy classes of paths joining x0 to a point here. Okay, so yeah, set wise, these two collections of homotopy homotopy classes, yes, they are the same. No, I mean, nasıl? Tamam. Tabii çünkü her bir petin de unique lift'i var ya. Unique lift'i. Evet, unique lift'i var. Her bir petin unique lift'i var. Yani fikir şu. Bu nesne homotopy classes of paths in X tilde. So there is a one-to-one correspondence between the points of X tilde and homotopy class of paths in X tilde, starting at a given point. Starting at x0 tilde. And the homotopies fixes the endpoints. And this thing is in one-to-one correspondence via homotopy lifting and curve lifting theorems. Homotopy classes of paths in X starting at x0. So I can just build my covering space as the set of homotopy classes of paths in X starting at x0. Okay, that was the idea. Actually, we just used in this example. Okay, here I considered actually elements of the fundamental group, but you don't have to do that. But so in particular elements of the fundamental group, they are also homotopy classes of paths, right? But these paths are actually loops. So those paths just correspond to some branches or trails in this tree, and yeah, that gives us a description of the covering space. Okay, now let's formally define X tilde now. Bu anlaşıldı mı? Yani bu bence muhteşem bir fikir, çünkü hani so this is a very great idea. Why is that? Because you construct the covering space of a arbitrary space without actually knowing description of this gadget. Yeah. So once you have this covering space, then of course you can build any structure, and we will do that. Any structure here to a structure here, because this map will be a local homeomorphism. Yeah. Okay, now formally we define so the covering space, the universal covering space P X tilde to X as follows. So as we said, X tilde is defined to be this gadget, homotopy classes of paths such that this path starts at X0, where homotopies fixes the fix the endpoints at all times. So if this path, let's say, goes from X0 to X1, then any other gadget, let's say prime, representing the same homotopy class, is homotopic to this one as follows. So there's a homotopy from gamma to gamma prime. At this end we have X0, and at this end we have X1. Okay. All right. Now, so we have defined X tilde set-wise. As a set, we know what it is, but it should be a topological space. So I have to define a topology on this. So, efendim? Yeah, the map P is okay. We can define P also. P is defined by how? So the image of this will be what? Well, of course, it should be this endpoint. So it should be just gamma 1. And this is a well-defined map. Why is that? Because if I have two representatives for the same homotopy class, then I know that the endpoints of these two paths are the same. Therefore, this is a well-defined map. So I have defined X tilde and P. Now we have to define the topology on X tilde. So topology on X tilde. So what is this topology? Okay, let's see. Okay, so we must show that. Okay, now let's put a topology on X tilde. Let U denote the collection of paths no, path connected, sorry, path connected open subsets of U such that pi 1 U into pi 1 X is trivial. By the assumption our space is locally simply connected, therefore every point has such a neighborhood. Actually, every point and every neighborhood of that point has possibly a smaller neighborhood which satisfies this condition that the inclusion map induces the trivial map on fundamental groups. Okay, so we have a huge collection of such path connected open subsets. Now, if U is in this collection and V is any subset, open subset, so that V is contained in U, then of course open, well, of course I should say path connected, open path connected, path connected subset V. Then of course we have the following. The map from pi 1 V into pi 1 U, right? Because of the inclusion map goes through U, we have this composition. So the inclusion map of V just goes through the inclusion map of U. And since this map is trivial, right? Trivial homomorphism, this map is trivial. thus V is also contained in this collection. So what we have seen is the following. If I have an open set in this collection, and if I have any other open path connected subset in X that is contained in U, then that open set also belongs to this collection. Okay. Efendim? Evet, this should be X. Tamam. Ee, ha, yani aşağıda evet, evet, evet. Evet, evet. Yani covering space'in ne kadar yani local homeomorphism olduğunu bilmiyoruz ya. Yani bir yere kadar local homeomorphism ama bir yerden sonra değil. Ee, yani şöyle hani küçük bir open set'te local homeomorphism ama şimdi sen aşağıda neighborhood'ları alınca o neighborhood'ların bazıları büyük olabilir. Yani öyle şeyler de yapılabilir ama muhtemelen eee, şimdi tam hatırlamıyorum bu nerede çıkıyordu ama yani bu işte eee, tam hatırlamıyorum da şimdi görürüz. Şeyde muhtemelen ya bu basis işlerinde falan. Uh, first claim is that this thing is the basis uh, for uh, uh, a topology. Bir dakika. Now, for the topology on X, bu X'in topoloji için bir basis veriyor. Şimdi basis olması için ne gerekiyor? For this thing to be a basis for the topology on X, we have to prove the following. For any so we have to prove two things. If X is in X and X is in W, an open subset, then there should be one element, right, in this collection. But then by the assumption, then by the semi-locally simply connected assumption, then there is some what W, no U open, so that X is in U, U is in W, and pi 1 U into pi 1 X is trivial, Okay, so this U is then, this U is in, therefore this U is in this collection. So what we have seen is then for any point here, an open set in open set around this point. I have an open set in my collection, which is contained in this open set, and it contains X. So that's the first condition of being a basis, right? Every neighborhood of any point has a neighborhood in that collection that is contained in that open set. Okay. The second part of the conditions for a collection to be a basis is that if we have two open sets in that collection, suppose I have a point in X and this point is contained in the intersection of two sets where each of these is in this collection, then I should be able to find a third open set in this collection which contains X contained in this union. Okay, how we do this? Okay, again, since X is simply simply connected, SSSC. Okay. There is some X, no, there is some U, so that X is in U, U is in U1 intersection U2, and okay. Well, since this implies U is in U1, but via this property, since U is in this collection and U is contained in this open set, and thus by the above observation, U is in U. So we are done, right? If I have any open set, semi locally simply connected, semi-locally simply connected. Evet, SLSC. Hence, hence, U is a basis for a topology on X. But our aim was to find a basis for a topology on X tilde. So we have to define that basis. Now, zamanınız var mı bu arada? Yokmuş. Okay. Let's stop. So next time I'll continue. Okay, so let me stop here.